Hello everyone, welcome back to our channel, Jacobian Engineering. Today our topic is Jacobian and homogeneous function. So this chapter is based on partial derivative. You need the concept of partial derivative. So if you don't know how to calculate partial derivative, please go to our playlist and see the video first. So let's start. So what is Jacobian? If f of xy and g of xy are two differentiable functions in a region, then the Jacobian of f and g with respect to x and y is the determinant of delta f by delta x, delta f by delta y, delta g by delta x, delta g by delta y. This determinant of the partial derivative of the functions f and g with respect to x and y is known as Jacobian, and it is written as del of f comma g by del of x comma y, or simply j of f comma g by x comma y. Okay, now see, if there are three differentiable functions, that is f of x y z, g of x y z, and h of x y z, then Jacobian of f, g, and h with respect to x, y, z is the determinant. It will go in the same manner, that is delta f by delta x, delta f by delta y, delta f by delta z, delta g by delta x, delta g by delta y, delta g by delta z, and delta h by delta x, delta h by delta y, and delta h by delta z. Okay, and this is written as del of f g h by del of x y z, or j of f g h by x y z. Okay, if there are more functions, then this definition can be extended. Now let us see our next topic, which is chain rules for Jacobians. Let us say this. So we have a theorem regarding this. So let's see the theorem. Let Z1, Z2 be two differentiable functions of y1 and y2, which are themselves differentiable functions of x1 and x2, then del z1 z2 upon del x1 x2, you can write it as del z1 z2 upon del y1 y2 into del y1 y2 upon del x1 x2. Okay, these z1 and z2 are the functions of y1 and y2, and these y1 and y2 are the differentiable functions of x1 and x2. So that's how you can write in this manner. And Jacobian regarding this would be del z1 by del y1 del z1 by del y2 del z2 by del y1 del z2 by del y2 multiplied by del y1 by del x1 del y1 by del x2 del y2 by del x1 and del y2 by del x2. That's how you can write it, right? We already know that del f of g by del xy can be written in this manner. So we can write this function as this in this determinant form and this partial derivative in this determinant form. Okay. Now remember one thing, that del z1 z2 upon del x1 x2 can be written as 1 by del x1 y2 upon del z1 z2. Okay. Now moving forward, this should be del x1 x2 by del z1 z2. So let us see some question. Our first question is, if x equals to r cos theta, y equals to r sin theta, then show that del r comma theta upon del x comma y is 1 by r. Okay, we have to show this. Now see, from this we can say that if we square and add both the sides, x square plus y square would be r square cos square theta plus r square sin square theta. If you take r square common, it will be sin square theta plus cos square theta, which is 1. So we can say that r square is x square plus y square. And if we divide, we'll get tan theta as y by x. R sin theta by r cos theta. R and r will cancel out. It will be tan theta. That would be y by x. So from this, theta is tan inverse y by x. Now let's differentiate this equation partially with respect to x. So when you differentiate it with respect to x, then y will be constant. Okay. Now twice r into delta r by delta x, that should be twice of x, and y is constant because we are differentiating with respect to x. So we can say delta r by delta x is x by r. Now what is x by r? That is cosine of theta. And if we differentiate with respect to y, that is partial differentiation. So twice r delta r by delta y, that should be 2y. And here x will be constant. So delta r by delta y would be y by r. Now what is y by r? That is sin theta. This is sin theta. Now what will be delta theta by delta x? So let us find out delta theta by delta x. So we can, this will be here minus y by x square plus y square. Now this is because, see here, from this theta is tan inverse y by x. Okay. Now if you differentiate both the sides with respect to x, then y will be constant. So here delta theta upon delta x would be, for tan inverse y by x, this is tan inverse x format. So it will be 1 by a square plus x square. Okay. So we can say that this is 1 square plus y by x whole square. And for y by x, we can say y is constant. and 1 by x is x to the power minus 1. So it will be n into x to the power n minus 1. So here 1 minus will be there and 1 by x square. So if we simplify, it will be x square plus y square. This x square will go in the numerator and we have minus y by x square. This will cancel out. So we'll get minus y by x square plus y square. Okay, this thing. Now y is r sin theta. So you can say minus r sin theta and x square plus y square is r square. So you can say this is r square. 1 r will cancel out. So it will be minus sin theta by r. Similarly, if you differentiate theta tan inverse y by x, tan inverse y by x, that is delta theta upon delta y, then x will be constant. So you can say this is 1 by 1 square plus y by x square, and 1 by x is constant. So it will be 1 by x multiplied by delta y by delta y is 1. So here we will have nothing. So if we simplify this, it will be x square plus y square, and x square will be in the numerator. 1x will cancel out. We will get x by x square plus y square, and x is r cos theta. X is r cos theta, and x square plus y square is r square. Okay. So 1 r will cancel out. It will be cosine of theta upon r. So let us see our what is, because we have to calculate delta r comma theta upon delta x comma y. So it will be delta r comma theta upon delta x comma y. So you know Jacobian related to this, delta r upon delta x, delta theta upon delta x, and delta r upon delta y, delta theta upon delta y. Okay, now we know all the value. Delta r by delta x, delta r by delta x is cosine of theta, so it will be cosine of theta. Delta theta upon delta x is minus sin theta by r, so this is minus sin theta by r. Delta r upon delta y, this would be sin theta, and delta theta upon delta y, it will be this cosine of theta by r. Now if we solve the determinant, it will be cosine of theta multiplied by this minus this thing. So cosine of theta multiplied by cosine of theta by r minus of minus sin theta by r into sin theta. So it will be cos square theta by r. This will be minus minus plus sin square theta by r. So if we take 1 by r common, it will be sin square plus cos square theta, that is 1. So this is the thing we have to prove. Okay. Now let us see another question. If u is x square minus 2y, v is x plus y plus z, W is x minus 2y plus 3z. Find delta u v w upon delta x y z. Here we have to calculate. We know that delta u v w upon delta x y z can be written in the Jacobian format, which is delta u upon delta x, delta u upon delta y, delta u upon delta z. Next, delta v upon delta x, delta v upon delta y, delta v upon delta z. Next, delta w upon delta x, delta w upon delta y, and delta w upon delta z. So let us find out all the values. So delta u upon delta x. So if we differentiate this, that is partial differentiation with respect to x, y would be constant. So differentiation of x square is 2x. And delta u upon delta y. So in that case, x square will be constant. So we'll get minus 2. Delta u upon delta z, that is there is no z term, so x and y will be constant, it will be 0. Similarly, we can say delta v from this equation. Delta v upon delta x would be 1. Delta v upon delta y would be 1. And delta v upon delta z would be 1. Similarly, from this equation, we can say delta w upon delta x is 1. Delta w upon delta y, which is minus 2. Delta w upon delta z, which is 3. Now we know all the values. So let us put in this determinant. It will be 2x minus 2, 0, 1, 1, 1, 1, minus 2, and 3. So if we solve the determinant, you will get, let us solve. We know that this is plus minus plus, and we are expanding along the first row. So it will be twice x, this thing minus this. So 3 minus of minus 2, that is 3 plus 2. Sign is minus, and minus of minus 2, that is plus 2. And if we are solving this, we have to remove this row, column, and this row. So it is 1 into 3, this 3 minus 1 into 1. And if you solve this, plus 0 into something would be 0. So it will be 10x plus 4. This is the required answer. Okay. So all these problems are similar. You have to be very cautious about finding the partial derivatives. Now our next topic is homogeneous function. Homogeneous functions. See, a function f of x, y, z in this way is said to be a homogeneous function of degree n if f of px, py, pz, you are writing in this manner. You can write t to the power n f of xyz, where t is independent of xyz. So this format is known as homogeneous function. Okay, so and we can say there is an alternate form. The alternate form is a function f of xyz is said to be a homogeneous function of degree n if f of x y z can be written as f of x y z can be written as x to the power n phi of y by x z by x in this manner. So let us see some example. Let us say we have f of x y z function as root x root y root z. Now let's put in place of x y z tx ty tz. So f of tx ty tz would be square root of tx plus square root of ty plus square root of tz. So if we take root t common, so it will be square root of x plus square root of y plus square root of z. So this is our function. So we can say this is t to the power half f of x y z. So this function is a homogeneous function of degree 1 by 2. And if you want to take example of the second format, so let us see one example. Let us say we have a function of xy which is xy by x cube plus y cube. Okay, so let's divide by x cube in numerator and denominator. So it will be xy by x cube divided by x cube plus y cube by x cube. So you can say we keep 1 by x outside, so it will be x to the power minus 1, and x will cancel out, it will be y by x divided by, this is 1 plus y by x whole cube. So you can see that we have represented the function as y by x. Okay, and we have x to the power minus 1 outside. So this is a homogeneous function of degree minus 1. Now let us see our next topic, which is Euler's theorem. Euler's theorem. So let us see theorem 1, which is for first order. The theorem is if f of xyz be a homogeneous function of degree n, then x into delta f by delta x plus y into delta f by delta y plus z into delta f by delta z, there should be n into f of x y z. Okay, so this is our Euler's theorem for first order. So remember this, and if we want to see theorem 2, and this theorem 2 is for second order. So if f of x, y, z be a homogeneous function of degree n, then for second order derivative you can say x into del x plus y into del y plus z into del z whole square. F is n into n minus 1 into f of x, y, z. Okay. So let us see examples to clarify these two theorems. Let us say we have a question something like this. Verify Euler's theorem and you have to verify the first order. This is first order for the function u of x comma y, x cube plus y cube plus 3x square y plus 3xy square. Okay. Now let us see if it is a homogeneous equation or not. So for this, let us put tx and ty in place of x and y. So u of tx ty would be tx cube plus ty cube plus 3tx square into tx plus 3tx into ty square. So it will be t cube here, here it will be t cube, and here it will be t cube. So if we take t cube common, it will be x cube plus y cube plus 3x square, 3x cube, 3x square, I think this is ty, 3x square y plus 3xy square. So this is our function u of xy. So we can say this is t cube u of x comma y. So we can see that it's a homogeneous function of degree 3. So u is a homogeneous function of degree 3. So for first order, we have to verify that x del f del x, y del f del y, z del f del z should be n times f of x, y, z. That's why we have found out the value of n here. So x del u del x plus y del u del y, that should be n times, that is 3 times u of x comma y. Okay. Now let's find out the partial derivative first. So del u by del x, that means here y will be constant. So this should be del x of x cube. Our function is x cube plus y cube plus 3x square y plus 3xy square. So y is constant, remember. So differentiation of x cube is 3x square, here y is constant, so it will be 6xy y is constant, so it will be 3y square plus 3y square. Now let's find out del u by del y. That means here x will be constant. So del y of x cube plus y cube plus 3x square y plus 3x y square. Y is constant, so x will be 0. This is 3y square plus 3x square plus 6xy. Okay. Now, according to the theorem, let's multiply x with del u by del x. So, x del u by del x plus y del u by del y would be multiplying here with x. It will be 3x cube plus 6x square y plus 3xy square plus multiplying this with y. It will be 3y cube plus 3x square y plus 6x y square. Okay. Now, if we take 3 common from this, so it will be x cube plus y cube, x cube plus y cube plus 3x square y, 3x square y. Here we have 3x square y and 6x square y. So 9x square y. We will have 3x square y here and 3xy square, 6xy square, 9xy square. And if we take 3 common, it will be 3xy square. So this is our function u. So we can say this is u of x comma y. So hence Euler's theorem is verified for first order, right? Now let us move forward and see another question. If u is tan inverse of x cube plus y cube upon x minus y, find the value of x square del 2 u upon del x square plus 2xy del 2 u upon del x del y plus y square into del 2 u upon del y square. So let us verify this. Let us find the value of this. So our answer, let's see the answer. Here it is given that u is tan inverse of x cube plus y cube by x minus y. So what would be tan u? So tan u would be x cube plus y cube by x minus y. Okay. Now if we divide by x cube, it will be 1 by x square. Let's divide by x cube. So x cube plus y cube by x cube, x minus y by x cube. So it will be 1 plus y by x whole cube, and if we divide by x, we will have 1 minus y by x, and we remain with 1 by x square extra, so it will be multiplied by x square. So we can see that tan u is a homogeneous function of degree 2. So you can say tan u is a homogeneous function of degree 2. Okay, so we can say, according to Euler's theorem for first order derivative, it's x into del x tan of u, that is the function f, plus y into del x of tan u, that should be n times the function. So n is 2 tan u. So let's differentiate this. If we are differentiating with del x, and u is a function of x and y, right? So what we can do, we can derive this function as del u of tan u into del u by del x. So if we differentiate this with u, that is this thing, it will be derivative of tan u is x square u multiplied with del u by del x. Similarly, here we have to apply the same method. It will be y sec square u into del u by del y equals to twice tan of u. So ultimately we get x del u by del x plus y del u by del y. If we divide by sec square u, then that means 1 by cos square u. So this is sin u by cos u. 1 cos u will cancel out. So ultimately we get twice. Okay, let's break this first. Sin u by cos u. And this is 1 by sec square u, that is cos square u. Okay. So 1 cos u will cancel out. So it will be x del u by del x plus y del u by del y. This is 2 sin u cos u, that is sin 2u. Now if we can see that here you have partial derivative with respect to x and y, right? So let us derive this equation 1 with respect to x and y. So we have to take the partial derivative of this equation with respect to x and y. So it will be u into v rule for x. Derivative with respect to x is 1, keeping del u by del x as it is, plus keeping x, del x of del u by del x would be del 2u by del x square, plus here you have to apply u into v rule. So if you are differentiating with x, that means y is constant. So directly we can apply the differentiation methods. So y into, this would be del x of del u by del y. That means del 2u by del x del y. We are differentiating with x. So here sin 2u differentiation is cos 2u, and 1 2 will come outside, and differentiation of u is del u by del x. Okay, and differentiating equation 1 with respect to y, we will get this is x is constant for y. So it will be x del y of del u by del x. It would be del 2u by del x del y plus we have to apply now u into v rule. So for y it will be 1, keeping del u by del x del u by del y as it is, plus keeping y it will be del 2u by del y square. If you are facing any problem how the partial derivatives are being done here, go to our playlist of differentiation, okay, partial derivatives, and you will see that everything will be clear. So this is y into del 2u by del y square, and here differentiation of sin 2u is again cos 2u multiplied with 2, and it will be del u by del y. Okay. Now let us say this is our equation number 2 and this is our equation number 3. So multiplying with equation 2 with x and adding by multiplying equation 3 with y. So we'll get, we are multiplying this equation with x and this equation with y. So let us multiply first. So if we multiply here with x, we will get x del u by del x, and this is done. Here we are multiplying this equation with y. So combining these terms, this will be y del u by del y plus this is x square del 2 u by del x square plus twice xy del 2 u by del x del y plus okay, because here you will have xy del 2 u by del x del y, and here you will have xy del 2 u by del x del y. So we will have twice xy del 2 u by del x del y, and from this you will get y square del 2 u by del y square, and this is equals to, you are multiplying this with x and you are multiplying with this y. So taking 2 cos 2u common, you will have x del u by del x plus y del u by del y. Okay. Now let us see x del u by del x plus y del u by del y is sin 2y. So here in this we can write that this is sin 2u plus this is x square del 2u by del x square plus twice xy del 2u by del x del y plus y square del 2u by del y square. This is again this is sin 2u. So 2 cos 2u sin 2u. Okay. Now if we take this term in the right hand side, it will be x square del 2u by del x square plus twice xy del 2u by del x del y plus y square del 2u by del y square. This should be, if we take sin 2u common, it will be 2 cos 2u minus 1 into sin 2u. And this is, we can say that cos 2 theta, we know the value of cos 2 theta, that is 2 cos square theta minus 1 or 1 minus 2 sin square theta. So in place of cos 2u, we can write 1 minus 2 sin square u. So we have cos 2u, this should be 1 minus 2 sin square u, and here we have 2 multiplication. So twice cos 2u would be 2 minus 4 sin square u. 2 minus 1 is 1. So 1 minus 4 sin square u sin 2u. Okay. Now this is the value. We have to find this value. This is our required value. You can keep it here or you can simplify further. That is up to you. Okay. Now let us see another question. If u is x times f of y by x plus g times y by x, then show that x times del u by del x plus y times del u by del y is x times f of y by x. And you have to show also x square u xx plus twice xy u xy plus y square u yy. This is 0. So let us see the solution of this question. And this is a very important question and it repeatedly comes in your exam. So let v of xy is x into f of y by x and w of xy is g of y by x. So v is a homogeneous function of degree 1, right? So we can say v is a homogeneous function of degree 1. So by Euler's theorem, we can say that x del v by del x plus y del v by del y, that should be n times the function. N is 1, so 1 into v. So this is the equation we got. Let us say this is our equation 1. And if you notice here we have x to the power 0. So that means w is also a homogeneous function with order with degree 0. So we can say w is a homogeneous function of degree 0. So from Euler's theorem, we can say x del w by del x plus y del w by del y. This should be n times n is 0 times function. So ultimately we get x del w by del x plus y del w by del y is 0. This is our equation 2. Now if we add equation 1 and equation 2, we will get x, and if we take del x common, it will be v from this term and this term. It will be v plus w, and from this term and this term, if we take y del y common, it will be v plus w. There should be v plus 0, that is v. Okay. Now here we can see that u is v plus w, right? U is v plus w. So you can say that v plus w is u. So this is x del u by del x plus y del u by del y. This is, and v is x into f of y by x. Okay. So see, v and w are homogeneous function. So you can apply second order Euler's theorem, which is, so you can say, since v and w are homogeneous, so by second order Euler's theorem, we will get x del x plus y del y square multiplied with the function v. That should be n into n minus 1. So order of v is 1, right? Order of v is 1. So 1 into 1 minus 1 into the function v. This is 1 minus 1 is 0. And for w, we can say second order derivative would be x del x plus y del y square multiplied with w. This should be, order is 0. So 0 into 0 minus 1 multiplied by w. This will be 0. So let us add these two equations. Let us say it is our equation number 3 and 4. So let us add 3 and 4. So from this we can say that these terms is equal. So if we take common, x del x plus y del y square with v plus w, that should be 0, and v plus w is u. So you can say x del x plus y del y square u, that should be 0. Okay. Now see, from this we can say that this is x square del 2 u upon del x square plus twice xy del 2 u upon del x del y plus y square. This is a plus b whole square formula. Y square del 2 u by del y square. Okay. If you apply here a plus b whole square, it would be a square plus 2ab plus b square. So for a square, it would be x square del 2 by del x square, and u will be come inside, and 2xy into del 2 u upon del x del y into u, and this is b square, so y square del 2 u upon del y square. That should be 0. So you can say this is x square and this is your uxx, y is xy, this is your uxy, and plus y square, this is your uyy. That should be 0. So this is our second proof we have done with, and this is our first proof we have already done. This is our first proof. So I think you have got the point how to handle this type of questions. Okay. So now practice 5 to 10 questions on your own, and if you face any difficulty, let me know in the comment section, and if you need more sums me to upload or more questions to upload, kindly refer the comment section. I will definitely help you. So that's all for today. Thank you. Have a good day and take care of yourself.